Good day everyone, my name is Kate Bilid of BSCE 3A, and today I'm going to present to you my performance task number 8 in ECE 23. And today I will teach you how to compute for entropy using Shannon's entropy equation. Now what you're going to do is use your first name and surname as individual reference. So my name is Kate Bilid. Arranging this in an alphabetical order, we are going to have A, B, D, E, I, K, L, O, T, T. And combining the similar letters into one, we are going to have A, B, D, E, I, K, L, O, T. So that's 9 letters. Alright. Based on the resulting letters or symbols, we are going to determine the following. We are going to design 2 different binary machines. Find the probability of occurrence of each letter based on your binary machine. And then we're going to compute the entropy using the 2 methods and compare the results on a summary and draw a conclusion on which machine is better. So let's take a look at binary machine number 1. You see, I already designed my machine. A yes represents a 1 and a 0, a no represents a 0. So what we're going to do is find the occurrence of each letter based from this machine. And then we are going to compute the entropy using the 2 methods. So first, let's determine the number of bits by tracing up the path. So for letter A, it is 1, 1, 1. So it's 3 bits. So what is the probability of having 3 bits? It's 0.125. It is determined by having this formula, which is 2 raised to negative n, where n is equal to the number of bits. So 2 raised to negative 3 is equal to 0.125. This also applies to letter B, D, E, I, and letter O and T because they are all 3 bits. Now, for letter B, it is 1, 1, 0. For letter D, it's 1, 0, 0. For letter E, it's 1, 0, 1. And for letter I, it's 0, 1, 1. And for letter K, it is 0, 1, 0, 1. For letter L, it is 0, 1, 0, 0. And for letter O, it is 0, 0, 1. And for letter T, it is 0, 0, 0. Now, using the probability method in determining the entropy, we are going to have this equation. So the answer is 3.125. Now, recall in the second method, we are using this formula. So the answer is 3.125. So it's the same results as the first method. Alright, we are done. Let's go over to the second binary machine I designed. So same as the first one, let's determine the number of bits and solve for the probabilities using this formula, where n is the number of bits of each letter. Alright, so A is 1, 1, so it's 2 bits. So 2 raised to negative 2 is equal to 0.25. This is also the same with letter L. For letter B, it is 1, 0, 1, 1, 1. So that is 5 bits. So 2 raised to negative 5 is equal to 0.03125. This is also the same for letter D. Alright, so for letter D, it is 1, 0, 1, 1, 0. For letter E, it's 1, 0, 1, 0. So that is 4 bits. So 2 raised to negative 4 is equal to 0.0625. This is also the same for letter I and K. Excuse me. Now for letter I, it is 1, 0, 0, 0. And for letter K, it is 1, 0, 0, 1. For letter L, it is 0, 1. For letter O, it is 0, 0, 1. And for letter T, it is 0, 0, 0. So using the probability method, we are going to have this answer, 2.8125. And in the second method, in determining the entropy, we are using the Hartley equation or Hartley function given by this formula. So solving this, we're going to have the answer of 2.8125. So it's the same as the first method. Now, let's summarize. For machine number 1, our entropy is 3.125 bits. And for machine number 2, our entropy is 2.8125. Okay, so we have computed our maximum entropy, which is 3.9925. So how did we get this answer? We solved it using this formula. So it is equal to H equal to log base 2 times M, where M is the number of your resulting letters. So mine is 9, so log base 2 times 9 is equal to this. Next, for machine number 1, code efficiency is 0.986. And for machine number 2, it is 0.887. So how did we get this? We simply use this formula. Just simply divide the actual value of the entropy to the maximum entropy. So let's say, for example, machine number 1, 3.125 divided by 3.169925, it is equal to 0.986. And for machine number 2, it is 2.8125 bits over 3.169925, which has a result of 0.887. So for the code redundancy, let's just simply subtract 1 on the code efficiency. Alright, so 1 minus 0.986, it has a result of 0.014. And for machine number 2, it is 0.113. And from this data, machine number 2 has the lowest entropy, which is 2.8125 bits, meaning it is more efficient compared to machine number 1 because it has the lowest value. So it has a better or higher redundancy compared to the machine number 1. So our interpretation is that machine number 2 will be the most predictable. It has a higher probability of predicting the correct outcome. So its result is least random. And less information needed to be transmitted to get the desired outcome. Because in machine number 1, it has higher entropy. Meaning the higher the entropy, the more frequent are signaling errors. So that's all for today. I hope you get the discussion. Thank you.